For number one, we're going to graph a function and then talk about its domain and range. And so you can use your graphing calculator to graph this and you'll get your result. You need to also be aware how this graph is related to its underlying function, which is x squared. And page 271 in the book, at the end of 2.7, page 271, it talks about graphing techniques and how to do shifts and reflections and stretches. So what we have here is a +4 inside the function, inside the x squared part, which means every single point on this graph is going to be shifted left 4. So picking one point to start with, the vertex, you would shift it left 4, and that's what we have on our new graph. The vertex is left 4. And then the +8 at the end, it means every single point goes up by 8. And you can see here our vertex is up at y equals 8, where on the original graph it was at y equals 0. So every single point on this graph, whatever point you have, left 4, up 8, and you get a point on the new graph. Now for the domain, if you look at page 205 through 207, it talks about domain. In general, we assume every single x value is in the domain, from negative infinity all the way to positive infinity. The only reason an x value would not be in the domain is if you plug in that x value and it causes a division by 0, or you plug in that x value and it causes the part underneath the square root to be negative, because you can't take the square root of a negative number, you can't divide by 0, so if an x value causes one of those things, we have to exclude it from the domain. But there's no division here, there's no square roots, so every x value works. No matter what x you plug in, pick any number you want, plug it in, you will get an answer. You will get an output, a y value. So our domain is negative infinity to positive infinity. Now for the range, again look at page 205. It is all the y values, all the outputs of the function. So you can see from our function that the smallest output we can possibly get is the value 8, y equals 8. The graph doesn't go any lower than that. 8 is the smallest y value, but the graph keeps going up and up and up forever. There's no limit to how big of a y value you can get. If you want a bigger y value, just put a bigger x value in here and you'll get a larger y value. So our range goes all the way up to infinity, but it's limited at the bottom at the number 8. So 8 to infinity. And a little talk about these brackets here. Since 8 is an actual output, we use the bracket. It shows that 8 is included in the domain. If you plug a 0 in for x, 8 is your actual answer. If 8 wasn't an actual answer, but it was the cutoff spot, like we could get every number up to 8, like really, really close. We could have 8.2, we could have 8.1, we could have 8.00001. Any number as close to 8 as we want, but just not quite 8, that's when you use the parentheses. And we'll encounter situations like this later in the class when we have asymptotes and we have our graph getting really, really close to a value, but it never quite reaches that value. So that's why we have to use parentheses instead of a bracket. And with infinity, we always use parentheses because infinity is not an actual number. You're never actually going to plug an x value in here and get the result of infinity. So we never actually reach this number, so we use parentheses with infinity. On number 2, we're going to be using the quadratic formula. It is on page 117. This is a formula hopefully you can memorize. So for a quadratic equation, you need to identify a, b, and c. A is the number in front of x squared. Here it's the number 1. We don't write it when it's a 1, but it's the number 1 there. B is the number in front of x, so it's a -14, and c is the value out at the end without an x next to it, so 74. and then plug those in the equation where they go. And then be careful to pay attention to negative signs. That's the biggest mistake people make. And just carefully reduce this expression here. So negative of a negative 14 is a positive 14. You take a negative number and square it, it's going to be positive. And then we have minus 296 for this part. So reduce further. Do that subtraction, you get minus 100. So now we can't take the square root of a negative number unless we talk about complex numbers and introduce I, which is the square root of negative 1. Imaginary numbers or complex numbers. So negative 100, you can rewrite that as 100 times negative 1. That's the same thing. Anytime you have a multiplication under a square root, you can do the square root of each part separately. So that's what I did here. And we can do both of these square roots now. Square root of 100 is 10. Square root of negative 1 is that imaginary number I. So we have this. And if you divide, actually do this division here, the top divided by 2, you get 7 plus 5i. And so both our answers have an imaginary part, 7 plus 5i and 7 minus 5i. The reason we get these imaginary results is because the graph of our parabola never actually reaches the x-axis here where y is equal to 0. And we were trying to solve for when it's equal to 0, and since it never is equal to 0, our only solutions are imaginary. And number 3 here, we're talking about shooting a rocket upward from the ground. And we have a quadratic equation to determine how high it's going to be in terms of t, which is time. So measured how far after the time we shoot it, how high it gets. H is the height. And we're trying to find the time interval is going to be higher than 235.2. So I'm actually going to find the 2 times that it's exactly at 235.2. And then based on that, we can find out the interval when it's higher than that. And so I'm going to subtract 235.2 from both sides, and now I'm going to use the quadratic formula to solve this equation here. Our A value is negative 9.8, our B value, and our C value. Plug all those into the formula. Pay very close attention to your negative signs, and let's reduce here. So we square that value, and here we're going to end up with a negative 9,219.84. And our bottom is negative as well. And reduce, do the subtraction. And then we can actually take this square root, and it comes out to 19.6 perfectly, which when we actually do this division now, divide everything on top by negative 19.6, we get a positive 5 plus or minus a negative 1. So if you do 5 plus the negative 1, you get 4. 5 minus the negative 1, you get 6. So those are the 2 times when the rocket is exactly 235.2 meters above the ground. And an illustration really helps us see that the time that it's higher than 235.2 is going to be in between those 2 time frames. So anytime more than 4 seconds up until any time until it reaches 6 seconds. And so as time passes, the x-axis here is the passage of time. So as we move to the right, time's passing, the rocket's going higher and higher and higher. And at 4 seconds, it's reached 235.2. So anytime over 4 seconds, it's above that height, then it starts to come back down. And once it's reached 6 seconds, it's back down to 235.2 again. And so we don't want to use the less than or equal sign for either one of these, because at 4 and at 6 seconds, remember we solved for when it was exactly equal to 235.2. But our problem wanted us to find the times when it's higher than 235.2. And so it's only when it's between 4 and 6, not when it's actually equal to 4 and 6, that we are actually higher than that height.